Welcome back, students, to our third lecture of thermodynamics. So in the last class, we used the first law of thermodynamics to say that if the internal energy of a system changes, it must do so through heat or work. Mathematically, we wrote that delta U, which was our change in internal energy, was equal to Q plus W. So work or heat can enter or leave a system. And if we can describe those two terms, we can figure out how the internal energy has changed. There's a reason for this notation that we have delta U equals Q plus W. We don't have changes in heat or work. We talked about this a little bit last time in noting that heat and work are transitory properties. So they occur during a change, but there's not a change in heat or work. To successfully work with these terms, we are going to need to be able to define state functions and path functions, and that is what we are going to do today. The learning goals for today are going to be to differentiate between state and path functions and be able to describe what is a state function and what is a path function, and so on. And in the process of this, we're also going to talk about reversible and irreversible processes and discuss the differences between those as well. Let's start by looking at state functions. State functions are best thought of as normal functions. And what do I mean by a normal function? Well, these are functions that obey the rules of mathematics that we have learned in all of our math classes up until this point. So for example, we have our U, our internal energy, and that's a function of temperature. If we want to figure out the change in internal energy, what we need to do is figure out what the internal energy is at temperature 1 and 2, and we can calculate that. And in the most cases, what we're going to be doing is evaluating these integrals to figure this out. And we discussed this a little bit last time, but since the heat capacity is approximately temperature independent, this integral boils down to n CVM times delta T, T2 minus T1. So in this case, to figure out the change in internal energy for a process, all we need to know is the final temperature T2 and the initial temperature T1. Nothing else matters. This has a property that kind of seems silly, but isn't true for path functions, as we'll see in a minute. So we have the cyclic integral of du is equal to 0. Now, you may not be familiar with this term cyclic integral there in this notation. Essentially, this is going to be an integral from T1 to T1. And we know that integrals represent the area under a curve between 2 points. So if the point is the same, there is no area under that point. So it's obviously 0. The cyclic integral of all state functions are 0. As we'll see, this is not true for path functions. So let's go through a little bit of an example here. Consider a state where we start at a certain spot. So this is our T1 here, represented by this pink circle. Now we have a T2 as well. We can consider many different paths going from T1 to T2. And since our internal energy is a state function, the path doesn't matter. So we can consider a path where we go between T1 and T2 in a straight line, and this will have a certain delta U associated with it. We could also consider another path, a crazy path. We can see here we still start at T1 and end at T2, but the path is very different. Nevertheless, it has the same delta U because the initial temperature and the final temperature are the same. So some maybe real examples of this that we've experienced. An example of a state function could be the net distance you traveled. So this is physically an x-axis. We could say, well, I started here and ended here, and maybe this distance in between is 100 feet, and I traveled 100 feet in this process, regardless of the path. The path function then would be the number of steps that you took. And we can see that the straight path will have the shortest number of steps, and this more circuitous path will have the longer number of steps. Nevertheless, they have the same net distance traveled between the two. However, there are a different number of steps. So that's basically what's going on here with heat, work, and internal energy. Let's go over some notation that highlights the differences between state functions and path functions before we get into what a path function really is. A state function is denoted by capital letters, as you can see here. So if we have a variable that gets a capital letter, such as internal energy, temperature, pressure, enthalpy, we'll see many more over the course of the semester. This is an indication that these are state functions. These state functions are able to be differentiated. So we can see this in terms of du, dp, dt, dh. We can also see this as delta u, delta t, delta p, and delta h. So we can have a change in any one of these processes from state 1 to state 2. Path functions don't follow these same rules. They have different rules. So to denote this, we give them lowercase letters. So the fact that we have a lowercase q and a lowercase w reminds us that our heat and our work are path functions. They are not state functions. We also can't differentiate them. And so to highlight this, we have a different set of notation. We'll use a funny sort of D. So this is the kind of D I'll use when I'm doing things in PowerPoint. You'll see the kind of D I write in class. I'll write it up on the board. And this represents that these are not real differentials that we can evaluate. We can say, how does delta U change from state 1 to state 2? We can't really say how does the heat change from state 1 to state 2. There's a heat associated with that process, but there can be many different values of heat that satisfy that integral, so we can't really have this. So we use this funny D here when we want to talk about differentiating one of these path functions. And we also will never write a delta Q. That's not something that we're going to write. We'll just have a Q or a W. So what do we do with path functions? We've seen how state functions work, and they seem to be like normal functions. So how can we have a non-normal function? So a state function, like we talked about before, is any function for which a change only depends on the initial and final conditions. We use temperature as an example. There are other examples. We could also consider pressure, volume. It could be distance, like we talked about, anything like that. Whereas the path function will depend on the path. So let's consider a state like this. So we have our initial state, a T1 here, where we have a gas in a cylinder and it has a mass on top, but that mass is being held back by a piston. We've seen this before by this stopper. So we have a P1, V1, and a T1 associated with this. Now we can bring this to an intermediary state by allowing the mass to drop and compress the gas. So if our mass drops, our gas is compressed, and we have a new pressure, new volume, and a new temperature as a result of this compression. Now, if we bring this in contact with our heat reservoir here, we will also change the temperature to temperature 3. They'll reach equilibrium. And this will not be able to change the volume because this piston is held in place, but it will be able to change the pressure. So we can have 3 different states here. Now, if we wanted to figure out the change in internal energy of this process, this intermediate state is irrelevant. We don't need to know that it ever crossed into P2, V2, T2. We just need to know it started at P1, V1, T1 and ended at P3, V2, T3. And that's enough information for us to figure out how the internal energy changed as a function of this process. That is not true for path functions. So path functions are any functions for which a change depends on the path taken. So we'll go through some examples to see this, but the work to get from this first state to the second state, and then the work to get from the second state to the third state is not the same as the work to get directly from this state to this state over here. It's in fact different, and it depends on the path taken. And there's also many different possibilities for how this state in state 1 here could have gone to state 2. And there's a lot of different values of work that can be associated with the transition from state 1 to state 2. So work is an example of a path function where we need to know how the system got from state 1 to state 2, or state 3 in this case. And it's not enough to know those final states. I want to take a brief second here and talk about the idea of internal equilibrium. Internal equilibrium is basically a fancy way of saying that our systems obey the ideal gas law. And that is going to be an assumption that we make for all of our thermodynamic processes. So here, this is a 3-dimensional representation of the ideal gas law. You see the relationship of pressure, volume, and temperature here. And what we're saying is that even though our system is changing, we're going from one state, initial state, to a final state, we're changing from state 1 to state 2. As we do this, our system is always going to do this by following the ideal gas law. So it's not going to start at the initial state, jump up here to an impossible state, and then jump back down to the final state. It's going to follow some path along this equation of state. And this is called a quasi-static process. So this is in general true. You can imagine scenarios where it wouldn't be true for maybe a certain number of nanoseconds. So for example, we could take a balloon inside of a box. where the balloon has a different concentration of molecules or so forth in the box. If we pop this balloon, there's going to be a brief second in time where the system is not at equilibrium, but eventually it will reach equilibrium with an equal concentration everywhere. We are going to not be considering this kind of intermediate state. We're going to be always considering states that obey the ideal gas law, follow the equation of state. Even when systems aren't actually obeying the ideal gas law, they will still obey some other equation of state that maybe reflects their properties as real gases or so forth. And I mentioned this before, but these are known as quasi-static processes. And a quasi-static process is one in which the rate of change of the macroscopic variables is negligibly small, such that the system is always at internal equilibrium and therefore always obeying the ideal gas law. All right, now let's jump to the whiteboard and go through an example to kind of try to piece together these differences between state and path functions. Consider the change shown here on the board. We're going to start with the gas that is occupying a 10-liter cylinder, then that gas will be compressed to occupy only 1 liter. We might want to know how much work is done in this process. And so what do we need to know? Well, we know the initial conditions, we know 10 liters, we know the final conditions 1 liter, but work is a path function, so that information is not enough for us to figure this out. We actually have to go and solve for the work. We saw in the last lecture that we had an expression for work, that work was equal to the negative integral of the external pressure, dV, the change in volume. So we're on to something here. We know the initial and final volume, but what is the external pressure? The external pressure can really be anything that could possibly accomplish this compression. And we're going to start by assuming a couple of things. First, we're going to investigate isothermal processes. So remember, an isothermal process has a delta T equals 0. So that means that we have T1 here, and we also have T1 over here. So what could the pressure be that would accomplish this change? Let's assume that this gas is under an initial pressure, in this case, of 1 bar. Now, since the temperature isn't changing, we know from the ideal gas law that P1 V1 equals nR T1, and we also know that P2 V2 is equal to nR T2. Since T2 is actually T1 and the number of moles in this case isn't changing, these two things are the same, and we can say that P1 V1 is equal to P2 V2. This is actually Boyle's law, which preceded the ideal gas law. So that means that P2 is equal to P1 V1 over V2. And in this case, we can plug in numbers here. This is going to give us 1 bar times 10 liters divided by 1 liter. So that means our P2 is simply 10 bar. So we can imagine in order to compress the gas down to this size, we must be using an external pressure of at least 10 bar. If we were using an external pressure of less than 10 bar, we wouldn't actually be able to accomplish this. It wouldn't compress it enough. So let's go through a couple of examples of how we could figure out the work. We're going to start by considering a case where we use a constant external pressure. Now, what I mean by constant external pressure, if I can spell it right, is that we have the same pressure for the whole course of this transition. So we're going to start by compressing this gas. Maybe we do that by adding a large weight, and that weight adds an additional 9 bar of pressure such that the total pressure is 10. Now our external pressure went from being 1 bar to 10 bars. This is one way that we could do this compression. How would we evaluate the integral work is equal to the negative integral of P external dV? Well, it's actually pretty easy because our external pressure we decided was constant. So if we're trying to evaluate the integral of P external dV, our P external is a constant number, and constant numbers don't change as a function of V. So we can rewrite this as negative P external times the integral of dV. And we can integrate dV, that's simply V. So what we end up with is then negative P external times V evaluated from V2 to V1. which is negative P external delta V. And this is one way we can calculate the work. So what is this? Well, we decided that our P in this case, that is negative 10 bar times 10 liters minus 1 liter, which is equal to 90 liter bar. We can use our conversion we saw last time, that 1 liter bar is equal to 100 joules, and say that this process had a work of 9 kilojoules. There was 9 kilojoules involved, or 9 kilojoules of work added to the system when we compress the gas in this way. This is not the only way we could do this compression. There are many more ways that we could do this compression. Let's consider another compression that we could do. So now let's imagine that we start at the same place. We start at a volume of 10 liters and a pressure of 1 bar. But now let's imagine that we have a two-step compression. So let's say first we compress down to half. So we have a volume V2 that is now 5 liters and a pressure 2 that is 2 bar. And then we have another compression that drops us all the way down to 1 liter. So the volume 3 of 1 liter and a pressure 3 of 10 bar. The temperature is the same for all of these steps. So now our path is different. We don't just go from 10 liters to 1 liter, we go from 10 liters to 5 liters to 1 liter. What is the work in this case? Well, in this case, the work is simply the sum of the individual works for the previous steps. So now our work is equal to work 1 plus work 2. And we can say that work 1 is the work associated with this step, and work 2 is the work associated with this step. So we can simply use the same integral that we did above and say that our work is equal to the negative integral of P2 dV minus the integral of P3 dV. Now, in this case, as the bounds are different, so for our first step, we're going from V1 to V2, and in our second step, we're going from V2 to V3. So we can integrate this in the same way as we did above and plug in numbers. What we'll end up getting is negative P2 times V2 minus V1, and then minus P3, V3 minus V2. So you can evaluate this expression, plug in our numbers here, and get the following. We'll find out that the work is equal to negative P2 is 2 bar, and our delta V there is 5 minus 10 for minus 5. And then our minus P3 is minus 10 bar, and our V2 minus V3 is minus 4. And so this gives us a work of 10 plus 40 liter bar, so 50 liter bar. And we can convert that into kilojoules as well, to say this is 5 kilojoules. So you'll note that same process, we're starting at the same state, we're ending at the same state. We have a work of only 5 kilojoules, whereas before our work was 9 kilojoules. We have a different amount of work because we've done a different path. If we wanted to calculate the change in internal energy, that would actually both be 0 because the temperature isn't changing. These kind of processes are known as irreversible processes. Now, when we call them irreversible, it doesn't mean that they are not actually reversible. So for example, if this process was done by adding first a small weight and then a larger weight, if we remove both of these weights, the system would revert naturally back to the initial state. So it is, in fact, possible to reverse our process here. What do we mean by irreversible then? What we mean is that energy has been expended that has not been absorbed into the system. So like we said last time, delta U for this case is equal to 0 because delta T is equal to 0. How can we have a non-irreversible compression or a reversible compression? So a reversible compression is going to be one in which there is no energy loss. In other words, we have an infinite number of steps. So consider this system shown here that's the same as the previous two systems. We have a gas and a piston. That gas occupies 10 liters of space and has a pressure of 1 bar. Instead of adding a large weight on it, or a small weight and then a larger weight, what if we had a beaker on top? And into this beaker, we added something fine, like perhaps water or maybe sand, and we added this water 1 drop at a time. Every time we added a drop of water, we're going to have a new external pressure that's going to cause this gas to compress. At the end of our compression, we'll end up with a gas that's compressed to the same state as it was before, and now our beaker is full of water such that it also adds 9 bar of external pressure, and we have 10 bar and occupy a V2 that is 1 liter. So how do we describe this scenario? What we do is go back to our integral and consider it. So our integral that we saw was the work is equal to the negative integral of P external dV. Now, what is the external pressure in this case? Well, it's not a number. So in the last 2 cases, we had first an external pressure of 10 bar. In the second case, we had an external pressure of 2 bar, followed by an external pressure of 10 bar. In this case, we have an infinite number of external pressures that are all varying. And we don't need to know what they are. What we can say is that for this reversible compression, the external pressure at every point is equal to P, which is the system pressure. So in the last 2 cases, that was not true. The external pressure was different than the system pressure until the system pressure reached the external pressure. Here, the external pressure is varying as a function of the system pressure. So now we have to integrate the integral of P dV. We can't pull P out of this integral because of the ideal gas law. We know that P is related to V. So P, the pressure of the system, is related to V, the volume of the system. And it's related to the volume of the system by PV equals nRT. So we can rewrite this integral as nRT over V dV. In this case, we are considering a system that has a constant number of moles and a constant temperature, so we can pull nRT out of this integral. We then have the integral of negative nRT times the integral of dV over V. And we're evaluating this from V1 to V2. We didn't see this integral much last semester. We'll see it a lot this semester. It is simply the natural log. How do we evaluate this integral? It is simply the natural log. So if we integrate dV over V from V1 to V2, we get the natural log of V evaluated from V2 to V1. So we could write natural log of V2 minus natural log of V1. However, what we're going to do is use our log properties to say that we take the difference of any 2 natural logs. That's the same as the quotient of those 2. So we can say that the work is equal to negative nRT times the natural log of V2 over V1. Plugging in numbers, we can figure out what this is. So here, work is equal to negative 1 kilojoule times the natural log of V2, which is 1, over V1, which is 10. And the you'll note here that this number is lower than either of our previous 2 numbers. And that is true in general. So the reversible work is always lower than the irreversible works. It doesn't matter what system we're applying this to. So let's go back to the slides to see some examples of this. Here we can see some PV diagrams that show the ideal gas law at constant temperature and how P and V change with respect to each other. So what's shown in this top panel here is a reversible expansion. And so this is a gas expanding under both reversible conditions and also irreversible conditions with constant external pressure. What we're doing when we do constant external pressure is we're evaluating P dV which is essentially taking the area of a rectangle here. So you can see when we're expanding, so if we started at this state here and expanded to this state at a constant external pressure, we would have to use this constant external pressure. And the amount of work that comes out of the system when we do this is shown by this rectangle here. And it is much less than the total work that we could theoretically extract from the system. And here we can see the same thing for the second step. As we add more and more steps, we see the following. We see that our work is becoming closer and closer and closer to the ideal reversible case. And we can say that the reversible work in this case is greater than the irreversible work. There's more area under this curve for the reversible case. Here is the compression, like we did the example about on the slides, and we can see that if we're compressing, we're starting at a high volume and compressing to higher external pressures. And in this case, the work that's done is greater than the reversible work. We have to expend more work than we need to in order to actually compress this gas. And so in this case, the reversible work is always less than the irreversible work. Since we have a sign convention for work, we can put these two things together. Here we're just looking at the magnitude, the area under the curve. But if we put these two things together, we end up with the following. We get that the reversible work is always less than the irreversible work. So that makes sense for this case down here. In this case up here where we had it the other way around, we recognize that when we're doing work, when the system is doing work, that work has a negative sign. So energy is coming out of the system. So what we're saying here is that the area under the curve for the irreversible case is smaller than the reversible case. And since these both refer to negative numbers, the irreversible work is a greater number technically than the reversible work. It is a lower magnitude negative number, which means it is in fact larger. We'll go through some more examples using PV diagrams in class. This will be a very helpful tool for us moving forward. The last thing I want to do, we talked about this throughout the whiteboard segment, but I wanted to show the definitions here of the irreversible and reversible processes. So reversible processes are defined as a process for which the direction can be reversed by adding an infinitesimal amount of the driving variable to the other side. And this is not true for an irreversible process. So again, as always with thermodynamics, the definitions are kind of obtuse. But what I mean by this is that for this reversible case, so for example, imagine in our example when we were dripping water. So we add one drop of water, drip, 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 it adds more weight, it compresses the piston. If I took away a drop of water, it would reverse without expending energy to go back to the state it was before. That's not going to be true if I smush it down with a heavy weight. So these are our definitions of reversible and irreversible processes. Keep these in mind, ask questions in class if you're not certain about what they are. We're really going to want to be able to have these settled in our minds as we progress forward in this class.